In previous videos for Chapter 9, I introduced the reactions of alkyl halides, which are essentially two: nucleophilic substitution and elimination. And then we concentrated a little bit more on nucleophilic substitution and learned about the nucleophiles and the kinds of reactions that they do. Now we want to get more into the nitty-gritty and learn about the mechanisms of nucleophilic substitution. And notice I said mechanisms. There are actually two. So the reaction can go by what's called an SN1 mechanism or by what's called an SN2 mechanism. These mechanisms are so important that they actually have names, SN1 and SN2. Sometimes it happens by an SN1 mechanism, sometimes it happens by an SN2 mechanism, and sometimes both mechanisms are very in effect at the same time. And we will learn how to predict when the SN1 mechanism and when the SN2 mechanism are in effect in a future video. But today we'll just introduce what is the SN2 mechanism and how do we know that certain reactions go by the SN1 mechanism. I mean, experimentally, how do we know a particular reaction is going by an SN1 or by an SN2? So just to review, here's the overall reaction for nucleophilic substitution. Nucleophile with a pair of electrons forms a bond to a carbon group, and somehow or other the bond to the halogen is broken and it ends up as a lone pair on the halide that comes off. So basically this pair forms a bond, this bond breaks. The question is, what order do those things happen in? Here's a possible mechanism. The mechanism is one step. So interestingly, the mechanism is the overall reaction. Notice there's the overall reaction. There's the one step in the mechanism. This is what's called a concerted mechanism. In other words, everything happens at once. So the reaction is all done after one step. So what has to happen is this pair of electrons has to come in and form a bond with the carbon. At the same time, this pair of electrons is breaking and going off onto the halogen. So it's kind of like one comes in, the other one goes out at the same time. It's all sort of a flow of electrons. This is what's called the SN2 mechanism. What does SN2 mean? Well, it's short for bimolecular nucleophilic substitution. The two means two molecules, or bimolecular, involved in the rate determining step. Now, what's the rate determining step? In any mechanism, one of the steps has to be the slowest one that happens, and that slowest step then determines the overall rate of the reaction. In other words, the slowest step in any process determines how fast that process can happen. Well, in this case, it's very simple. Since it's a one-step mechanism, that is the rate determining step. So the rate of this step obviously determines the rate of the overall reaction. And notice that there are two molecules on the left-hand side of the arrow in that step, and therefore it's called bimolecular. In other words, the rate's going to depend on how much of the alkyl halide is present, and it's also going to depend on how much of the nucleophile is present. So it depends on two molecules, so it's bimolecular. This is actually something that can be measured. So physical organic chemists measure the rates of chemical reactions. This is the whole area called kinetics, and we haven't dealt a whole lot with kinetics, either in organic chemistry or in general chemistry, but it's a huge area of study, and it basically asks the question, what affects the rate of a chemical reaction? How can you speed it up or slow it down? Well, here's some data. So here's the experiment. Essentially, we start this reaction. We're going to take some methyl bromide and some potassium cyanide. We're going to put them together in a flask in such a way that we know their concentrations to begin with, and then we're going to measure the rate of the reaction. Now that is a mouthful right there. Measuring the rate of a reaction is not that simple, but for now we'll just not worry about how do we measure the rate. But if we put in 0.1 molar of methyl bromide and 0.1 molar of potassium cyanide and measure the rate, it turns out to be 0.0021 molar per second. Now I'll tell you a secret, I'm just making these numbers up, but essentially it's the kind of data that you might see in this experiment. So we've measured the rate of the reaction. We throw that away and we start all over again, and this time we're going to put in 0.2 molar of methyl bromide and 0.1 molar of potassium cyanide. We can put in as much or as little as we want to, obviously. Even though the reaction is a one-to-one balance equation, we can put in twice as much methyl bromide if we want to. And when we do, and measure the rate, it turns out it's 0.0042. So doubling the concentration of the methyl bromide has doubled the rate of the reaction. Then we throw that out and start all over again. And this time we're going to start with 0.2 molar of methyl bromide and 0.2 molar of potassium cyanide. So we're keeping the methyl bromide the same, and we're doubling the potassium cyanide. And again, we measure the rate, and we find that it's 0.0084 molar per second. So again, it's doubled. So essentially what we found out is that doubling the concentration of the methyl bromide doubles the rate, and we found out that doubling the concentration of potassium cyanide doubles the rate. In other words, the rate depends on both substances. So we can write what's called a rate law, and it's always in the form of rate equals k times something. K is a constant called the rate constant, and we don't really worry about what it is, we just know that it's a constant. And what we find out is that the rate depends on the amount of this, and the rate depends on the amount of this. So they're both in the rate law. And notice that if k is a constant and you double this, you would double the rate. And if you double this, you would double the rate. And so both molecules are in the rate law. And that's really why it's called bimolecular, because there are two molecules involved in the rate law. So both the methyl bromide and the potassium cyanide, or both the alkyl halide and the nucleophile, affect the rate of the reaction, so it's bimolecular. And that fits perfectly with the mechanism, which says they're both in the rate determining step, or both on the left-hand side of the arrow in the rate determining step. Okay, so that's an experimental evidence for an SN2 mechanism. Here's another one. Think carefully about the three-dimensionality of this. Here's the alkyl halide, and it's tetrahedral with 4 groups attached, including the halogen. And what has to happen is that the nucleophile has to come in from the back, pushing that pair of electrons in to form a bond. At the same time, this pair has to leave and go off on the halogen by itself. Now, this is really important that the nucleophile has to come in from the back. It's what's sometimes called backside attack, sometimes called inversion, where whatever the configuration of this carbon was before, now it's flipped, essentially like an umbrella in the wind. So these 3 atoms, whatever they are, hydrogens or carbon groups or whatever, flip over like an umbrella in the wind, and so it's inverted. The configuration of the carbon is inverted because it's backside attack, and it's backside attack because it's concerted. The nucleophile has to come in at the same time the leaving group is leaving. So the stereospecificity of reactions that go by SN2 is called inversion. It's measurable. So here's an example. If we started with this alkyl halide, and notice that this is a chiral carbon, has 4 different groups attached, and because it has 4 different groups attached, we can indicate whether it's R or S. In this case, I've drawn it so it's R, so this is the R isomer. Then after the cyanide comes in, or whatever the nucleophile happens to be, in this case I've chosen cyanide, it flips over, and now it's the S isomer. So notice that this methyl was up and pointing a little bit to the left. Now it's up and pointing a little bit to the right because it's flipped over. This hydrogen that was pointing down and back and a little bit to the left is now down and back and a little bit to the right. Again, it's flipped. And the cyclobutyl group that was down and to the left is now down and to the right. And so the bromine that was attached on that side is now replaced by a cyanide attached on the other side. So it's inversion. Here's another example. Here we have 4-methyl chlorocyclohexane. So chlorine and a methyl group, 1 up and 1 down. So this is the trans isomer. If you react this compound with the hydrogen sulfide ion, it turns out that you get the cis isomer. So the chlorine that was pointing down compared to the methyl group is now pointing on the same side compared to the methyl group. So again, it's an inversion. In this case, it's like mirror images, sort of like enantiomers, where an R isomer becomes an S isomer. In this case, these are actually like diastereomers, where a trans becomes a cis, but nevertheless, it's still inversion. Okay, and then a third factor that we can actually observe, again, just to go back and review, we can observe the kinetics of a reaction, we can measure it, and we can see that it's bimolecular when the mechanism is SN2. We can see that you get inversion when the mechanism is SN2. And furthermore, the third thing is that we can literally see that no rearrangements happen in an SN2 mechanism. So notice that in this case, the bromine is on a primary carbon next to a tertiary carbon. When you react it with the hydrogen sulfide ion, you get the sulfur going on the same carbon that the bromine was on, not on the tertiary carbon next door. In other words, it doesn't rearrange. That's always true in an SN2 mechanism. Not so much in an SN1, but in an SN2 mechanism, no rearrangements happen. So basically there are 3 things. It's bimolecular kinetics, it's inversion of stereochemistry, and no rearrangements can occur. Those are all pieces of evidence for an SN2 mechanism. So here's an example problem. What I would like you to do is, looking at this reaction right here, see if you can draw the mechanism for the reaction, include curved arrows, and that's going to make it a little bit trickier because you got to draw it in such a way that the curved arrows will actually point towards the bonds forming and bonds breaking, and then also give the rate law for this reaction. So stop the video, take a few minutes, write out the mechanism, write it once if you want to, just in a simplified form, but write it again showing curved arrows, and then finally see if you can write the rate law for the reaction. And I will reveal the answer now. Okay, so here is the mechanism. it is essentially the same as the overall reaction. So if you just wrote down this reaction for the mechanism, that would be fine, but it doesn't show curved arrows. So what I've done here is redrawn this molecule. So the bromine is pointing specifically over to the right, and then I'm bringing in the hydroxide in on the left. I'm showing a pair of electrons from the hydroxide attaching onto this carbon. At the same time, a pair of electrons from the bromine is leaving. And again, you could have written this in any number of different ways on the paper, as long as you showed somehow that a pair of electrons from the hydroxide is pointing in here to the space between the carbon and the oxygen. And then another pair of electrons from this bond is moving off onto the bromine. And notice that the bromine then becomes minus, and hydroxide then becomes neutral hydroxyl group. And then the rate law is simply rate equals K. That's always the first part of any rate law, times the concentration of the alkyl halide. And if you wanted to draw out the alkyl halide like that, or just write it as RBR, that would be fine. And then also the concentration of hydroxide is in there. Like any math equation, it doesn't matter which one you put first in the rate law. Problem 2. Assuming the mechanism of the reaction is SN2, draw the product, write its complete mechanism, and give the rate law. So this time I'm not asking for any curved arrows, just to predict the product. So stop the video and I will reveal the answers now. So first of all, what is the product? Well, essentially you're going to replace the bromine with the ammonia, and of course the nitrogen is going to become positive because it will now have 4 bonds to it. This is a neutral nucleophile. But since the methyl group here is pointing up and the bromine is pointing up, ammonia comes in to replace it. It's going to come in from the bottom, and the bromine is going to leave from the top, and so the new NH3 plus group is going to be on a dotted line. If it was on a wedge, it's going to be on a dotted line. That's that whole inversion thing. And of course, Br minus then would be the counterion for that, and you should write that in as a byproduct since this is a balanced equation. Here's the mechanism. Boom. Same as the overall reaction. It's just a one-step mechanism, and that's easy as long as you don't have to draw curved arrows. And then what about the rate law? Well, the rate is equal to K, there should be a K in there, times the concentration of the alkyl halide times the concentration of the ammonia. So again, both substances are in the rate law. And that's the end of the video for today. Thank you very much.